As I promised, I said I was going to explain my implementation for this problem. But first, let's get all greens on camera, okay? So it works like when you run it, the test case. And yes, I know Usiko, it's not if you get a test case, you get the cases right. We've seen that so many times where if you get it right, you get everything else wrong. But the logic is correct because, like, compared to the solution, and the solution is very similar. I feel like in my opinion, I'm not. I just think my functions were cleaner, like the and my variable names were cleaner than the solution three. The solution three is basically my logic, but yeah, I just think it was cleaner. But anyways, let's just submit it like just these functions. But essentially the same thing, doesn't matter. All right, so let's submit. Let's get all greens on camera. Let's get all greens on camera. Easy. Give me the green. Give me the green. Give me the green. All right. But what if you get trolled? Nah. If okay, yeah. Okay. Okay. Yo, bro. Why is it going slow? It's kind of sus, dude. The grade is going extra slow. All right. I don't know why these cases are going so slow. It's just binary search. It's definitely passed. It's like n log n. All right, cool. So it works, right? Um, and I'm going to be basically, if you understand the logic, the implementation shouldn't be that bad. Like, if you really understood the logic, like, when I mean understand, like, you understand every nook of the logic, then implementing it is a piece of cake. Like, the only problem I had is the first time I tried it, I had infinite loop in the binary search, and I was about to debug this stuff, but I was like, before I debug any functions, because I knew these were like coded properly, that there's like no way I'd mess that up because code's not that complicated. I was like, so apparently, if you add like a one to here, you get infinite recursion. Or not infinite recursion, you get an infinite loop and it doesn't work. And I don't really want to explain why. Like, this problem's already a handful enough. So I don't really want to explain that. But anytime you have that type of problem, just try to do like plus one, minus one. And here you do plus one, here you don't. So it's just some weird stuff. Just test. Just remove the one or add the one. Just test both and just see if you get like, yeah, just do it. Because like it's annoying to think about. So basically called the class Angry CG, Angry Cows Gold, right? Buffer reader, print writer, you take an N, and basically we're going to have a set. Remember, we talked about how we're going to scale each position by two. Like I said, watch the logic video because I'm not going to re-explain logic here. I'm just explaining the implementation. And then we have the low radius and the high radius. Basically, what we're going to do is we're gonna binary search the answer, right? But we're gonna before we binary search, binary search the answer. We need to binary search the optimal position for a given radius because remember we're gonna take these left case. There's for a given radius. There's two cases. There's two optimal positions. It's the case whether you push it as close to the right or left end. We chose to push it as close to the right end, and basically we just binary search for like low start, high start of the collision. As represents start of the collision. Basically, if we can do the middle start of the collision, then we set low to mid s so we can like do it as much as we can. Else we set mid s to minus one, right? And can left is just a function, right? It's a monotonic function. And then basically, if once you pushed it as further as you as far as you can, um, once you push it as far as you can, then you just binary search the radius. So we have the optimal start position now, and then we just say if we can do the mid radius, if mid radius works, then we set high to mid radius because we're trying to minimize it, and else if it doesn't, then we set low to mid radius plus one. And then we print out our answer. Let's take a look at how this function works, the can left and can right function. They basically just simulate if a uh, if you could if a at a cow, can you explode all the cows on the left, and can you explode all the cows on the right? So like if can left, if can right. So basically what I do is I set a bound, which is basically this might require a little bit of drawing, just so you can understand it. But basically I set like a bound, right? So at a position, right, right, let's say this is P. You have P minus R. You basically want to look for a Hebel that's greater than P minus R. So let's say the Hebel is H. You want to look something for that's greater than P minus R, but less, but uh, less than P. So the bound is basically the range, and to do that, I use a set. So you find the greatest integer less than or equal to that bound, and you check if that bale or that integer is less than or equal to position. And if it is, then you move to the bale. So your position's at the bale. You subtract by 2 because we scaled everything by 2. Remember, and then after the bound, now you have a new bound, and then you just keep doing it, and you keep doing it uh, until position is first, or until position is first, or you break out of this if position's first, or you break out if you get like an invalid thing, and then you to check if it's invalid or valid, you just return position equal hey dot first, and essentially the can write is the same thing. In this case, you just basically do the for, because if you have a position P, then P plus R, you want to find an H such that H is greater than P, but or you want to find an such that H is greater than P, and then H is less than P plus R. And then you just apply the same exact logic you did for the can left for the can right, and that's just the code. So see you guys next time.